Next lesson. Implicit differentiation. All right, we're going to talk about why we need this. We're going to talk about how we do this. We're going to look at some cute pictures, and then we're going to differentiate inverses. Okay. All right, consider a circle of radius 5 centered at the origin. Okay. All right, we can describe the circle like so. Okay, and that's what's called an implicit description, okay? As opposed to an explicit description, which would look like this. Y equal to a function of x. Okay? So, we've described the relationship between y and x implicitly, okay? It's hidden in this equation, as opposed to explicitly, which would look like this, okay? And in fact, in this case, it's impossible to write it like this, okay? Because this is not the graph of a function, okay? It fails the vertical line test, okay? All right. All right. We can draw a non-vertical tangent almost everywhere on this circle, okay? And we maybe want to find out its slope. How can we do that using the tools of calculus? Given that we don't have something that looks like this. And some of you who know anything about geometry will know that if you want to draw a tangent to a circle, all you need is the radius and draw something perpendicular to that. Yep? But in general, that doesn't work for general curves, described analytically, so we use calculus. And how do we use calculus for this kind of problem? Okay. Suppose we want to find the slope of the tangent at minus 4, 3? Plus 4 minus 3. Plus 4 minus 3. Okay. Plus 4, not really. There-ish. Minus 3. Okay, so we want the slope of that tangent. Beautifully drawn. Okay? And again, for circles, yeah, the tangent is perpendicular to the radius. But that's kind of hard to generalize. Okay, so what do we do? Option 1. If necessary, decompose and write explicit functional relationships. Okay? So, you could write this as y squared equals 25 minus x squared. And then, from that you get y equals plus minus 25 minus x squared. Good? All right. This describes the upper semicircle. This, with the minus sign, describes the lower semicircle. Okay? This point is on the lower semicircle. Our point is here. Okay, so we can just take the derivative and that'll do it. Okay. Okay, what do we got here? We've got a composition. Okay, once we take care of the minus sign, we've got a composition of the square root and this thing. Okay, use the power rule, or remember that the derivative of the square root is 1 over 2 square root. So we get minus 1 over 2 square root evaluated at the inside, which is 25 minus x squared. Okay, multiplied by the derivative of the inside, which is minus 2x. Again, if chain rule is new to you, write it out explicitly every time until you get it, and ask me if you have questions. All right, the minus signs kill each other, the 2's kill each other, and we're left with x over root 25 minus x squared. Okay, we wanted the tangent at x equals 4. So evaluate at x equals 4. All right. 25 minus 4 squared is 9. The square root is 3. 4 over 3. Okay?
So essentially, explicit is like making an entire function out of like your given. Because like.
Yeah, or breaking it up if you have to. So you write y equals a function of x. Okay, and
implicit is just x and y.
They can be mixed up in some weird way, and you don't have y equals thing.
Okay.
Okay, so this might be useful if you deal with lenses and optics, and if you've seen any physics, you'll know that when you talk about the laws of refraction, you need the normal to the surface of the lens, for instance, right? And the normal is perpendicular to the tangent, so it's good to be able to know where the tangents are. So this is useful. Okay, that's one way. What's option 2? The point of today, implicit differentiation. Did I erase the circle? That's brilliant. That's really good. That's first rate. Okay, minus 3, 4. Easily replaced. Like some of us. Okay. All right, so basically what we're going to do is, we're going to treat the thing, okay, the curve, as the graph of a differentiable function around the point that we care about, okay? Right, so we pretend the curve is the graph of a differentiable function around the point we care about. But we leave it implicitly defined. We never explicitly write y equals anything. We don't do that, okay? So we're going to find dy over dx without ever describing y explicitly. Okay? All right. Very simple. Brilliantly, we've also erased the equation. So x squared plus y squared is 25. Step 1, differentiate both sides with respect to x. Okay. Derivative with respect to x. Okay, the derivative of a constant is 0. Don't forget that this is going to wind up being 0. And maybe I'll write this elsewhere. Okay? Now we need the derivative of this. Again, what did we say? Y is an implicitly described function of x around that point. Okay? So treat y as a function of x. All right, the derivative of this is the derivative of this plus the derivative of this. The derivative of x squared is just 2x. What's the derivative of y squared with respect to x? Again, y around that point is an implicitly described function of x. It's a function of x. We have a composition here. We need chain rule. Derivative of the outer function times the derivative of the inner function. You don't have to do all of this. If you do this in your head, brilliant. Okay? The derivative of the outer function, which is squaring, times the derivative of the inner function, which is just y. Okay, this guy is 2y by the power rule, and multiply that by the derivative of y. Okay? This will probably soon, if not already, happen in your head. Okay, step 1, differentiate both sides. Step 2, use chain rule and other rules. Step 3, solve for this. Okay, bring the 2x over there, it's minus 2x, divide that by 2y, and you get minus x over y. Okay, notice we now have a derivative with both x and y in it, which we didn't used to have. Okay? And that's common when you do things implicitly. What this does is, it's going to tell you the slope of the tangent anywhere, not just on the top bit, like the other method did, or the bottom bit, like the other method did, but everywhere. Okay? So if you just had x equals 4, that specifies 2 points and 2 different slopes. But because this guy asks you for x and y, it can pinpoint the point you're talking about and give you the right slope anywhere on the curve. Okay, and in particular, the point you cared about was what? 4 minus 3, so just plug that in. 4 minus 3, x is 4, y is minus 3, and you get 4/3 again. Which is good. Okay? Differentiate both sides, carefully apply the rules, including chain rule, and then solve for the derivative. Okay? Because you were looking for the derivative only at a particular point, what you could have done was, once you did this, just plug in x equals 4 and y equals minus 3, and then solve for the derivative. Okay? So just to show you how this works, we found the derivative at any point, and then subbed in.
Can you repeat the steps again? So, like, it's differentiate.
Differentiate both sides, use chain and other rules, and then solve for the derivative.
Alright, thank you.
Yes, sir. It's ludicrously easy to forget this. Okay? Don't forget this. Okay? Put lots of exclamation marks and highlight it. Okay. In many ways, this method is nicer. Okay? You don't have that stupid breaking up thing. It looks cleaner, and it works a lot more generally. Okay? It's not always possible to break up an implicitly described thing into 2 explicitly described functions. And sometimes when it is possible, it's a pain, and then differentiating that painful thing is also a pain. Okay? So being able to do this is very, very handy. What else? No, that's it. Okay. Where are the 2 points here that we have a problem? Where does the derivative not exist? Vertical tangents. Okay? Otherwise, it's smooth and lovely. But vertical tangents give us a problem because infinities give us a problem. So here and here, this thing's not differentiable, which is consistent with this. If I plug 5 into this, it gets upset. Okay? And if I plug 0 as y, this would get upset. Okay? So those 2 points are not in the domains of the derivative. Okay? The derivative does not exist where the tangents are vertical. Okay. Questions?
I just want to ask, why do we like use or like know when to use implicit differentiation?
When it looks implicit. Yeah, so when
Like,
you have
how do
y
we know
equals
if it looks implicit?
a function of x, then you do the normal thing. Yeah?
Like if it's like a word problem. Or
When you have a word problem, you have to model it, right, as an equation. And then depending on what the equation looks like, you do this or not.
Like if it's like a circle or like a function that is, that isn't a
You have to look at the equation. Whatever it is, you look at the equation. If the equation looks like y equals function of x, then you do what we always do. If you've got something like this, then you have to do this. You'll see examples. If you see enough stuff, you'll be used to it. Okay. All right. Hey guys, I'm going to have a fit of conscience about this if I don't say this. I'm not saying bio people are bad at math. Okay?
Right.
And I didn't actually compare, so whatever. Okay? I'm just saying if you want an excuse, that's a good one. To say physics people do more math. But these people are better than everyone else. And I'm one of you, so there we go. All right, here we go. All right, pretty pictures. All right, here we go. The volume of Descartes. Described by that. You don't have to know these things, all right? Okay. Implicitly described. Almost nice looking. Clearly not the graph of a function, okay? It fails the vertical line test miserably. Okay, but we could decompose it into the curves of three functions. The graphs of three functions. So for example, there's the graph of a function. There's the graph of a function. And there's the graph of a function. Okay, so you can break it up. Okay, it's a union of the graphs of three functions. So you could decompose it. Okay, and theoretically you can do option one here. Okay, but it's hellish. Okay, it's a lot easier to be able to do this implicit thing with an equation like that. Okay. All right. I don't understand this name. That doesn't look fat to me. That looks box-like to me. And those of you in zoology will be doing what? Cnidaria cubozoa. Yeah? That's right. Here we go. Just a fat circle. Just an example.
I don't even remember what that is.
Cube, box jelly. Okay, another one. A cardioid means heart-like, or depending on what kind of person you are, it looks like a butt. Yeah, well, yeah, kidney works too. Different strokes. Okay. You'd have seen this. You'd have seen this if you have microphones, and you see how microphones pick up sound in space. You might have seen that pattern. Okay, this guy is a function. Okay, this passes the vertical line test. Okay, and yet we found it easier to describe it implicitly. So you want to use the implicit way instead of annoyingly trying to write this as an explicitly defined function. And then this mad thing. Yes, you'll be expected to sketch. All right, I just put that up because it was cool. Okay? All right. All right, example. There was another example before. I might do it in a tutorial or something else. All right. But I'll do this one because it's maybe simpler. Okay, so what do we want to do? Find the slope of the tangent at 1, 3, the point 1, 3, to the curve described by the equation x cubed minus 3xy squared plus y cubed equals 1. Verify that point is actually on the curve, okay? If it's not, the person giving you this question is sick, okay? You plug x equals 1 and y equals 3 into here and make sure it checks out. Okay. We'll do the implicit way, because if I tried the explicit way, bad things would happen to me. So, differentiate both sides. I know I've made this mistake of forgetting this guy over here and just writing 1, okay? Don't forget to differentiate that to get 0. Okay, differentiate both sides, hopefully correctly. Get 0 as the derivative of a constant, and now deal with this mess. X cubed gives 3x squared. Minus 3 times a product. So you need product rule. Again, if this is unclear, ask me or work it out explicitly yourselves. All right. So it's a product of x and y squared. The derivative of the first, so the derivative of x, which is 1, times the second, y squared, plus x, the first, times the derivative of the second. The derivative of y squared. Don't forget, you need to do that. So that is, did I use prime notation? I'm going to use prime notation for this. 2y, y prime. Okay, so again, derivative of x is 1 multiplied by y squared plus x times the derivative of y squared, which as we saw over there is 2y times the derivative of y. Okay? All right. Plus the derivative of y cubed. So again, derivative of outside, 3y squared times derivative of inside, y prime. 3y squared, y prime. And that's equal to, as we said, the derivative of a constant is 0. Okay? Yeah.
Would you be able to break that down a little bit, please?
Yes, ma'am.
I'm very well set.
Yes, good. Thank you.
Thank you.
No problem. Okay, I'll break down that piece, yeah?
Yep.
Okay, so I'll just do that piece. Okay, so if you needed to do this, derivative of, thank you for asking, 3xy squared. Okay, I bring the 3 out. Okay, and with practice, this kind of stuff becomes very, very second nature. Okay, the 3 comes out, and here we go. That's a product. We need product rule. What does product rule tell me? Derivative of first, or use primes if you like primes. Derivative of first times second plus first times derivative of second. Okay, derivative of x is just 1. This guy, do just that again. Yeah? So this guy you get 2y dy over dx. Exactly like that. Okay. And over there, just for brevity, I wrote this as y prime. And that's it. That's all good?
Yeah.
Okay. Yeah, sure. Okay, and when we got to y cubed, we essentially did that thing again, except with cubed. Okay. All right, so we got this thing now. What do we want to do? Pretty it up, maybe? Okay, 3x squared minus 3y squared. Evan, help me if I make a mistake here. Minus 2 minus 6 xy primed. Okay, plus 3y squared y primed equals 0. Okay, we've asked you for the tangent, the slope of the tangent at a single point. So what you could do right now is you could plug x equals 1, y equals 3 into here, and then solve for y prime. Okay, you can do that. And there's nothing wrong with that. But I will do the other way this time, so you see it. Okay. Solve for y prime. So what have we got? Y prime. So the first step in solving, sort of isolate all the y prime stuff on one side, then factor out the y prime. So here we go. Y prime times 3y squared minus 6xy okay, and this other stuff comes to the other side. 3y squared minus 3x squared. Good? Just keep all the prime stuff to one side and then factor out the y prime. And then just solve. Okay, good. All right. We can do some nice things. We can divide top and bottom by 3, and we can factor if we like to. So we can write y minus x, y plus x, difference of squares, if you like. And then on the bottom we got y squared minus 2xy, factor out the y, and there we go. If we want to be cute. Good? Okay, and then we evaluate that x equals 1, y equals 3. Okay, what do we get? We get 3, okay. 3 minus 1 is 2. 3 plus 1 is 4. 8 up top. On the bottom, 3 times 3 minus 2 times 1, 3, 8/3. Good. Okay? So again, because we're asking you for the derivative at a point, you could plug in the point here and then solve for y prime, or if you feel like it, you can solve for y prime in general and then plug in the point. Okay? If we don't say at a particular point, you have to do it this way. All right. I've already drawn the tangent, yeah? So you can see that point that we cared about, and you can see the tangent, which I trust you will trust me, is the slope I promised. Just for fun, and if you're already confused, don't worry about this. Just for fun, notice when this guy gets upset. It gets upset if y is equal to 0 or y is equal to 2x. Okay? So, consistent with that, okay, that if y is equal to 0, y is equal to 2x, the derivative will be upset. When would the derivative be upset? If you have a vertical tangent. And look, where y equals 0 or y equals 2x cross the curve, you get vertical tangents. The world makes sense. And where's the derivative 0? If the top is 0. If y is equal to x or y is equal to minus x, then we get the derivative being 0. So where those lines cross the curve, you get horizontal tangents. Again, the world makes sense. If that's confusing, forget it or ask me. Okay? We did a first derivative. In tutorial, I'll possibly do a second derivative. Decisions. Hey, it's a challenge. I've got 2 minutes. Let's do it. Okay. Is this productive? You're free.
Okay, actually, do you have a little bit of time now?
Again, office hours today. I'll see you on Friday. Thank you. All right, guys. I wrote this a few times. I mean, I didn't write this. I said this a few times last time. I never wrote it. Please make sure you write this somewhere. When you're doing implicit differentiation, treat y as a function of x. Okay? Because there's a bunch of mistakes you can easily make if you don't do that. Okay, so when you do implicit, always treat y as a function of x. Okay, ready? And you can hear me, yeah, at the back? Or you want me to shut the door? Here we go. We are going to finish implicit differentiation. Derivatives. Guys, keep it down. Of inverse functions. Okay, we'll briefly handle this, and we can handle this easily using implicit differentiation. Here we go. For instance, let's prove that the derivative of the natural logarithm function is indeed the reciprocal function for x greater than 0. Okay. This guy looks friendly. It looks differentiable on its domain. Okay, and ln is going to be differentiable on its domain, which is that. So let's go. What do we do? Let y equal ln x. Okay, we don't know what to do with that. Let's rewrite it in the form we can deal with. That's the same as saying e to the y equals x. Okay, y is the exponent to which e has to be raised to give x. Okay, take derivatives of both sides with respect to x, treating y as a function of x. This is implicit differentiation. So here we go. What do we got? E to the y is the outer function, and the inner function is y. Okay, we're using chain rule here. The derivative of exponentiation, natural exponentiation, is just natural exponentiation. So we've got this. Right here. Okay, derivative of the exponential, the natural exponential is the exponential again. So e to the y multiplied by the derivative of the inside function, y prime, or dy dx. And the derivative of x with respect to x is just 1. Okay, any questions about that? Okay, we just do the implicit thing. Okay. And then, again, as we did before, we solved for the derivative, which is 1 over e to the y. We'd love to have this thing in terms of x. Looky, looky. E to the y is equal to x. And we're done. Okay? Okay, so we took the relation we had, we rewrote it, did implicit differentiation, solved for the derivative, and subbed back from here so that we got an answer in terms of x. Cool? Cute, short. Good? Okay, no questions? All right, and there you go, there's a pretty picture for you. And again, whenever I show you a picture, do me and yourself a favor and make sure that everything checks out. So if ln's increasing, the derivative better be positive everywhere. Okay. Well, there's a giveaway, isn't it? I ruined the surprise. Okay. Second example. We're going to find the derivative of arctan, or for those of you who prefer, tan inverse, quote unquote. Okay? Remember, arctan looks like this. It's differentiable everywhere on its domain. And its domain is R. Let y equal arctan x, exactly the same trick. Okay? We write the relation, then we rewrite it. What was the definition of arctan? And don't forget the restricted interval. All right. Good? Literally the definition of arctan. Okay, now what do we do? Same thing, implicit differentiation. The outer function here is tan. The inner function is y. Okay? Let's take a derivative. Instead of x everywhere yet. X, good. Okay, the outer function is tan, the inner function is y. The derivative of tan is secant squared. So we're using chain rule here again, as usual, secant squared of what it sees multiplied by the derivative of the inside function, multiplied by dy dx. The derivative of x with respect to x is 1. If any of this doesn't make sense or any of that doesn't make sense, tell me. Okay? Same deal as before. Solve for the derivative. dy over dx is equal to 1 over secant squared y. Which you'll recognize as cosine squared y, if you wanted to. Okay, again, we'd like our answer to be in terms of x. So what can we do? We have secant squared y. We'd like our answer to be in terms of x equals tan y. Luckily, we have an identity that does just that. Go over. Okay, we have an identity that says what? Recall. Or look on a sheet somewhere. Secant squared y is 1 plus tan squared y, okay? Which is just a Pythagorean identity with a little trick inserted. Okay? We've seen this before, yeah? Say yes. Okay. Let's see, what do? You have the, you have the Pythagorean identity, sine squared plus cos squared equals 1, and you divide through by cos squared, and you get this. Okay, so there we go. It's exactly what we want. So now we can rewrite this. So, dy over dx is equal to 1 over secant squared y is that, 1 plus tan squared y. Tan y was x. Beautifully, that's the answer. Okay? Same deal each time. Rewrite using the definition of the inverse. Take derivatives of both sides with respect to x. Don't forget to use chain rule when you take the derivative. Solve for the derivative. Use whatever tricks you need to get the answer in terms of x. And that's it. Same deal both times. Okay? Questions? All right. Again, this guy was differentiable on its domain, which was all the positive reals. This guy's differentiable on its domain, which is all the reals. What else do we want to say? If you find this business too baffling, it shouldn't be. It's just a Pythagorean identity dividing through by cos squared. But if you find it worrying, what you could do is you could draw a circle, let's say a non-unit circle, based on x equals tan y. Okay. It's too small. Okay. Based on x equals tan y. And what do? That angle is y. Okay, tangent is what? Opposite over adjacent. OA. So, or you can remember it as, oh, this is going to be confusing. Okay. You get that, yeah? OA, x over 1. Good? So you can draw a triangle. Using Pythagoras, you see that that side length has got to be the square root of 1 squared plus x squared. Yeah? And so cos y has to be 1 over that. So the secant has to be square root of 1 plus x squared. So the secant squared, excuse me. So the secant squared has to be 1 plus x squared. Cool. So for some reason you prefer this to that, you can do this. Okay? Does this make sense to anybody?
Yes.
Oh, good. Okay. Excellent. Again, tan was vertical over horizontal, you write that, then you find this, and from that you can see what the cos is. Okay. And then keep in mind you also have to make sure that that works for angles that are down here, and then you're done. Okay? But I figure it's a lot easier to just use the identity. Any questions? Where's my picture? Okay. Look at how smooth and beautiful and not vertical this thing is. So it is differentiable everywhere. What can we see? Any tangent I draw to the curve, which is the graph of the function, is going to have positive slope, or it's increasing. And so the derivative is positive everywhere. So that checks out. Notice where this guy is steepest. The derivative is maximum. So that makes sense. As we go, let's say, either way, arctan is approaching its asymptotes, its horizontal asymptotes, it's sort of stabilizing, and it makes sense then that the derivative would be approaching 0. Okay? As the derivative approaches 0, this guy flattens out. Okay? Everything makes sense. Yep.
I just don't get how like the last is like not 1 over 1 plus x squared.
Hmm?
Why like for like if you did it the other way, why wouldn't it be 1 over 1 plus x squared?
Because it's 1 over secant squared. So it's 1 over that.
Okay, so our final answer is
It's always that, yes.
yeah, but like
You plug this into there.
oh okay.
Yeah.
Oh right.
Yeah. Or you could write that in terms of cos, and then not even write any of this, and just use that.
Yeah, because we're looking for the sorry.
Again, I wrote this in case people prefer this, okay? If you don't prefer this, the identity works perfectly, okay? And I think it's a lot cleaner than drawing the picture and checking both cases and all this stuff. Okay. Good? Okie dokie. There's a thing called logarithmic differentiation, which I think is optional, so I'll do it in the tutorial briefly. Basically what you do is you take logs of both sides, use log rules to simplify, and then take the derivative, and then work through that way. And one thing that lets you do is find stuff that's stuff like this. The derivative, for instance, of x to the x, which is a weird thing we don't really have a rule for. Okay, so you can use logarithmic differentiation for that, or you can use a certain rewriting trick to do that. And I'll do that in the tutorial. Or something similar. Okay, this arctan thing, you can do it with the... Okay, the arctan thing you can do it with the other inverse trig functions. And look, I've written both forms so no one complains. And there you go, those are the derivatives. And the implied domains are the correct domains. Okay, and I may do one of those in tutorial as well. We've already done arctan. Okay?